for getting started in the Liskov substitution principle. What's the overall goal of the Liskov substitution principle from my comments last time? Or what is it that I indicated that we'd be studying? The last time that we talked about this sort of material, prior to the Python introduction, I had talked about type hierarchies. I talked about hierarchies of two sorts of constructs within Java, for example, or C# and other similar languages. And they were classes and they were interfaces. And in both cases, these are constructs that can be arranged in what we call type hierarchies. And these type hierarchies provide us with the ability to exploit what's called polymorphism. What is polymorphism? Does anyone remember? We say that a language supports polymorphism. What do we mean?
Casting to different types.
Sorry?
Casting to different types.
Okay, there's an element of casting involved. You can have a type, something that's of type B, and casting is not quite the right word, but it gets treated as something of type A.
It's like the object-oriented principle of if you have a car and a specific type of car, that specific type of car is still a car.
That's good. Good. So you can treat, so if we have, I'll take that example. We have a type of car, right? So maybe you're writing software for car dealerships or for manufacturers of cars. I know someone who made a minor fortune, doing consulting for GM, advising them on the rollout of different models in their fleet or what have you. And so we have a car here, and then we have various subtypes of car, right? So we might have Chevys, so Chevrolets. We might have GM vehicles. We might have Toyotas, and we might have Hyundais and many other types, right? And each of these in turn might have particular types. So Chevrolet might have an Impala and Cavalier and many other models, and GM similarly, and Toyota. And what this means, and Hyundai of course. So what this means is that with polymorphism, I can pass an Impala around as if it's a what?
A Chevrolet or a car.
Or a car. I could treat it as a car for certain types of needs. I could treat it as a Chevrolet for another type. Similarly with a Cavalier, because they're Cavaliers, but they are also Chevrolets, and they can be treated as Chevrolets and as cars. Now, why is that beneficial? I talked about it last time that we covered this material before the Python introduction, but it's important to understand why this gives value. Why is that useful to be able to treat Impalas as cars?
Because you can write like classes, methods, and functions and stuff that will be useful to things that haven't been invented yet later on.
So Royce, you put your finger on one of the most critical and arguably a little bit of a subtle issue. So not only can we reuse code that is written against car, that assumes properties of cars and treats things as cars, and therefore and by virtue of polymorphism, we can pass it any number of particular types, and it will operate correctly. Not only can we have code reuse, but we have extensibility, because having written this code against car, we can then extend our system in many ways without having to go back and change the code written against car. At least that's the promise. That's the potential and the promise associated with object-oriented programming. That we can write code once against a superclass, and then we could reuse it against all these different subclasses, for example, or subtypes more generally. Okay, so that's much of the promise of object-oriented software engineering. But it turns out, in order to secure that promise, in order to gain its benefit, in order to reliably, in order to be able to rely on it with confidence, there are certain properties that have to be maintained by these subclasses or subtypes to make sure that they are safe. with respect to being treated as a car. And that's what this Liskov substitution principle is about. Liskov substitution principle is named after a guiding light in the computer science field, Barbara Liskov, and it's often called. It's also often associated with the name also of another famous computer scientist, Jeanette Wing, who also was involved in formulating this together with Barbara Liskov. Okay, so suppose we have a subtype D, which is a subtype of C, and we have some function or method that takes in a C and uses it. And then we have some other code in our system which creates a D, a subtype of C, and it passes it into this method or function foo. So here we have something that's truly a D. Its actual type is the term I used last time. Type it truly is a D, but it's being treated over in foo as if it's a C. All right? It's being treated as a car where really it's a Chevrolet Cavalier. Yeah? And this code for C, if we extended C with another subtype E, for example, we could reuse foo, right, with that E. But the important thing to note is that we have somewhere within our code, we know it's a D, but for the sake of foo, we're treating it as if it's a C. We don't have recourse directly to what type it really is. Okay, so the Liskov substitution principle, ladies and gentlemen, provides a principle which allows us to reuse the supertype in a safe fashion by recognizing what a legitimate subtype is. It basically prevents us from creating inadvertently a fraudulent subtype that is going to break our system. That's going to break this code for foo, for example. It's going to violate its assumptions. And we talk about this being a principle to formulate behavioral subtypes. Subtypes that are not merely apparent subtypes claimed to the compiler, but in fact are legitimate behavioral subtypes where there's a genuine subtype relationship. So there's only so much of that the compiler is going to be able to check for you. Much of it you have to check, and this is why I'm teaching it to you. Because when you go out and you go into the world of software engineering, you will be responsible for checking the Liskov substitution principle with respect to your code. That's not going to be something checked automatically by the compiler. Okay, not all features of it a compiler can check. Okay, and the principle reflects the need to reason safely about types in the presence of polymorphism. So if we can pass around a D as a C, if we can pass around an Impala as a car, then what restrictions do we need? What guidance do we need? What guidelines do we have to adhere to do so safely? Okay. And the statement of the principle is fairly mathematical. I'll give it here, but I'm going to unpack it into more intuitive terms. Okay, so the statement is this. If there's a property provable about objects of the supertype, so in this case about C, or in this example on the board about a car, if there's some property which, looking at the definition of the car interface, the contract associated with car, or looking at the definition of the C interface, if there's something that you could be counting on, then that same property should be true of all subtypes. Okay? To avoid surprising anyone who's relying on the supertype, relying on the properties of a car, for example. So subtypes have to maintain guarantees that someone could reasonably infer from the supertype. In other words, subtypes have to stay true and consistent with the properties that are apparent from the supertype. So if you see a definition of car, and you could come to certain conclusions from that, those conclusions should be adhered to by any subtype here. If you could look at the definition of C and come to certain conclusions, those should be adhered to by the subtype D. Okay, that's the overall idea. Let's unpack this. Okay, let's turn this into some examples. And I'm going to be recurrently coming back to this situation where a developer is creating code with respect to something that has a parent type, but is actually a subtype of that. So let's consider someone writing foo. I have an apparent type C, but secretly, in this case, it's a D. Can you imagine that? Can you imagine that? I would note here that this relationship, subtyping, might be because D implements the interface C. Or it might be because D is a subclass of D. D is a subclass of C. Either one of those, it's a subtype. In either case, it can be passed around as a C, right? Just think about your knowledge of Java. Think about your knowledge of C++ or C# or any number of other languages out there. You can often achieve this subtyping relationship where you can pass around a D as if it's a C, either with implementing an interface, right? Implementing an abstract class would be another example, or take a subclass. A D is a subclass of C. Is that familiar territory for you? You can pass around one of these as these, right? So you implement the interface serializable as Java, and so you can pass around as something that's serializable. Or you subclass object automatically, so you can pass around whatever class you create as an object, right? Familiar stuff? Okay, so imagine we're writing foo. We have something that all we know is that it's a C, but secretly it's a D, right? And we're going to be reasoning about, to avoid breaking this code in foo, what has to be maintained? What has to sort of reliably be the case for us to write that code in foo and know it won't break whenever a new subtype is introduced, okay? For this code to be correct, when we introduce a new subtype, what constraints does that subtype need to adhere to, okay? So that someone who wrote foo isn't rudely surprised. Suddenly their code breaks because someone has introduced a new subtype E, or this new subtype D, which has broken these assumptions that foo has. That's the recurrent problem we're just being back to. And it's going to sound restrictive, but when you come down to it, it's common sense. And really, it's common sense to avoid bugs. It's to avoid rework. And at first, when you see some examples, you might think, man, this is really tying me down. It's really hampering me. And actually, it isn't that much if you really understand it. But it's a matter of documenting clearly what the assumptions are, and if you don't want the programmer to come to certain assumptions, making that clear. Okay. We're going to be taking a look at the Liskov substitution principle, not as a just kind of restriction that you should in theory apply, but as a very real thing that you should apply within your programs. Okay. So I got to come back to this key points for reflection in just a minute, but I want to consider an example from the real world here. Okay, example from the external world outside of computers, and that has to do with service contracts. Okay, so the idea here is we're going to have a delivery service. Okay, think about FedEx as a delivery service. FedEx allows you to set up FedEx franchises. A franchise will be associated with an office of FedEx that can put the FedEx logo on things, that can use FedEx infrastructure and provide FedEx guarantees, but it's actually owned by someone else. It's actually owned by someone who owns that franchise and stirs up business for it, etc. Okay? So the idea here is we're going to consider this sort of delivery service, and the question that I have for you here is, given that FedEx provides on its website and on its app and so on certain guarantees, if you get the package in by a certain time, that it will get that package to its destination, say Ottawa, by a certain time, what guarantees must a franchise offer to be legitimate? Okay, so suppose the parent company, FedEx in this case, has to drop off. In order for it to provide a guarantee, a certain guarantee, you have to drop off the package by noon. And if you do that, the delivery of that package will be by 5 p.m. the next day in Ottawa. Suppose that's its guarantee. You drop your package off by noon. we will deliver that package to auto, get it to its destination by 5 p.m. the next day. That's their guarantee. It's a service contract, okay? Okay, now you want to set up your franchise, and you're interested in not just adhering directly to their rules, but potentially changing things in a way that's favorable to the customer and to yourself. Okay, so for your precondition, would it be okay for the customer to drop things off, to provide the same guarantee as long as they drop it off by 3 p.m.? Would a customer have reason to be upset if that were the case? If you, for your franchise, allowed people to drop it off by 3 p.m. and you would make sure that it gets to Ottawa by 5 p.m. the next day, would that be okay for customers, as far as the customer is concerned? Think about it. So you're a customer, you walk into this FedEx franchise, and the person behind the counter, it's 11:59, and the person behind the counter says, "Oh, don't worry, you have plenty of time to fill out those forms. We actually, in this office, we allow you to drop these things off by 3 p.m., and we'll still get it to Ottawa by 5 p.m. Would there be any reason to be upset in this case? No. They've relaxed these guarantees, right? Now, it's up to them to deliver on them. Maybe they have a Concorde in their backyard, which they can take off and get it to Ottawa. Maybe they have a person who drives a very fast motorbike, and will get it to Ottawa by 5 p.m. the next day, even if you drop it off by 3 p.m. Maybe they send it on the Blue Flame or shoot it in a rocket. As long as it gets to Ottawa by this time in a decent condition, you'll be happy. And if they allow you to drop it off by 3 p.m., you'll be fine. Now, what would be problematic for the franchise is if you come into the door at 11:59 and they say, "Sorry, for this franchise, you have to drop it off by 9 a.m." Right? You could be upset, legitimately. You went to the website for FedEx, you used their app, and it says you have to drop it off by noon. You've scheduled your day around this, and now suddenly they're telling you, "Sorry, for our place, you have to drop it off by 9 a.m. We can't get it to Ottawa by noon." You could legitimately say, "What sort of FedEx franchise is this?" Right? This isn't FedEx. This is a fraud, right? Okay. Now let's consider it. So this is the precondition. This is a contract. There's going to be certain preconditions. They require you to have the package in to them by a certain time. That's the precondition, in which case they'll deliver on the postcondition. Let's consider postconditions. So obviously, this franchise could just adhere to the FedEx postcondition. If you satisfy the precondition, get it in by the appropriate time, we'll get it to Ottawa by 5 p.m. the next day. Let's consider alternative postconditions, okay? Suppose we had a franchise which guaranteed not just getting it to Ottawa by 5 p.m. the next day, but getting it to Ottawa by noon the next day. Would that be okay? Yeah, man. Come in. I'm really worried. I don't know if we'll get to there by close of day tomorrow. They sometimes close the government buildings at 4:30, and they'll say, "No, we'll guarantee it by noon." Would the person using the contract, the person using this mechanism, using FedEx, have reason to be upset? No, they have no reason to be upset. Their expectations by looking at the website or app for FedEx have been met, but even exceeded. All those assumptions they had that it would get there by at least 5 p.m. the next day have been met, but here it's even a stronger guarantee. You'll get here by noon. On the other hand, you'd be potentially quite upset at the FedEx franchise if they say, "Well, the delivery will be next year. We have a tortoise, and we'll put it on the back of the tortoise, and it will crawl to Ottawa, and it'll get there by next year." You'd be quite upset. Or if they say, "Well, we can't get it there for 2 days," right? So this is our FedEx delivery service. So let's consider this, okay? So here we have a sort of contract hierarchy. We have FedEx on the one hand, and they have a deliver method. And it has some precondition and has some postcondition. And then we're going to have subtypes of FedEx, these instances of FedEx. Franchise 1, franchise 2, right? And franchise 1 here, we have the package for its precondition. It just says package available by 3 p.m. And the postcondition is delivered by noon the next day. is this a legitimate subtype of this one? This is the question of the Liskov substitution principle. So suppose you were writing code that uses this interface based on this precondition and postcondition. Would your code break if this were the case? Would your assumptions break? If you were structuring your life around this FedEx contract, would your assumptions be thrown out the window and violated, and would you have a reason to be upset if you were using this FedEx franchise here?
Yep.
You would? Okay, so what would upset you?
Well, if you get it there at 1 p.m.
Okay. If you got it, so let's think through that case. So I welcome that. If you got it here at 1 p.m., a normal, what you'd expect from the website is, sorry, we can't get it till 5 p.m., not tomorrow, but the day after that, right? Because it violates the precondition. Okay, so it's really good to think these things through, and I welcome that comment. So if the precondition is not met, the postcondition is not guaranteed. So if you don't get it there by 12 noon for the FedEx general rules, you can't count on the postcondition being met. Effectively, what this would mean is it would get there not tomorrow, but the next day, right? Whereas for the subtype, it actually is met, but really the subtype just needs to maintain the assumptions of, if the precondition is met, what the postcondition is. So let's think this through. Is this subtype here, this FedEx franchise 1, is that legitimate? Would anyone have cause to be upset with this?
As long as your schedule was expecting the original, you'll be perfectly happy with that.
Precisely. So if your schedule was tailored around this, if you were counting on this contract based on the website, based on the app, and you came into the FedEx franchise 1, you'd have no reason to be upset. In fact, you might be happy, but you'd have no reason to be upset. It has if you were counting on this and suddenly you found out, oh, I have to use this particular franchise, which is dealing with FedEx franchise 1's rules, you'd have nothing to be upset about. Nothing's broken, right? Okay, by contrast, let's suppose you were counting on the FedEx website, counting on the FedEx app, and you got FedEx franchise 2 here. The package has to be available by 12 noon, and the package is delivered by noon the next day. Would you be happy there?
No.
Yes or no, do you think? I heard a mixture. Okay, so here we have the same precondition, and we have a tighter postcondition, right? The package, for counting on the website, you think it's delivered by 5 p.m., but this one guarantees it by noon. Would you have reason to be upset here? No, they provided an even stronger guarantee. Same precondition, but they provided a stronger guarantee. It's not that these franchises have to provide exactly this guarantee. They can provide something tighter, and that's perfectly legitimate. Let me ask another one, though. Suppose we have this contract hierarchy, and instead of these ones, we had a FedEx franchise 3. I can't fit it here. Here the package is available by 12 p.m. Is the precondition, and the postcondition is package is delivered by 8 p.m. the next day. Would that be a legitimate?
No.
No. Someone could be upset by that, right? They've structured their day around this. They plan to use FedEx because of this contract at FedEx, but they came in and they found that that contract isn't adhered to by the franchise. And again, they could say, you're not a FedEx, you're a fraud, right? You're not a real FedEx. What do you mean you're putting up this FedEx sign and so on? I'm counting on the FedEx rules and you don't abide by the FedEx rules. You break the FedEx rules. Okay, so this is the basic deal we'll be exploring here. Let's concentrate on this a bit. Okay. So the idea here, ladies and gentlemen, is that like in the real world with delivery services and contracts with companies and so on, interface specifications, the guarantees provided by pieces of our program, regardless of whether it's a function like we saw in that early Java code, or in Python, or whether it's a method and a class or a class as a whole. These are contracts, and when we have a specification, I argued in my lecture where I highlighted abstraction by specification that one of the main ways that we secure abstraction in our program, beyond providing parameters, we provide a separation of interface from implementation. We give a contract, a guarantee of what a system does. Maybe it's a method. And then that provides a specification that can be adhered to by any implementation. Remember, the idea with abstraction is it hides many particular details. There's many particular details that can all be met by this abstraction. And if we provide a specification, there's many implementations that can provide it, okay? And so a specification provides a contract that can be adhered to by any implementation. And who relies upon the specification? Well, the users, just like you going with that package to FedEx or counting on FedEx's rules. The people who use a contract like this guy here in foo, who's using C, they're relying on the specification of D, or C, excuse me, of C here. They're relying on the properties of C. Do you appreciate that? You understand what I mean? Foo is relying on C's behavior as promised through this interface. If you go look at the documentation, the specification for C that says what it does, foo will be relying on that, right? Just like if you go to the FedEx website, if you go to the FedEx app, you will be relying on the features of what's promised there. So it is with people who use an instance of an object whose specification is provided. They're relying on the behavior of the class as specified by that class. Okay. Now it turns out there's two other groups that will be counting on that specification as well. One is the creators of interfaces of subtypes. If you want to create a D, if you want to create an E, you'll be counting on the features of C, and then superclass creators as well. Okay. We'll be coming back to this last one later, but these first two are of central interest to us right now. Okay. Now, it turns out this problem doesn't go away if you don't provide specifications. It's just, then it becomes guesswork and it's just the promises are unclear. What we're going to be doing here is looking at what promises we need to make for subtypes to make them consistent with and safely used as if they're supertype, the instances of the supertype. Okay? So here, we're worrying about the promises made by the subtype, the promises made by the FedEx franchise. The promises made by the FedEx franchise in its relationship to the promises of the supertype, the promises of FedEx. That's what we're thinking about, right? What are the promises being made? Hey, where is it? Promises being made by these guys down at the bottom in light of the promises made by FedEx. And we're asking, what would cause someone to be upset if they're counting the problems of FedEx? What sort of franchise would cause big problems for them? Would deliver negative value? And what sort of franchise would be viewed as perfectly legit? That's the question we're getting to. So it turns out that the Liskov substitution principle, in order to adhere to it, you have to think of three types of issues. The first is method signature compatibility. In other words, the methods of the subtype, or the functions within it, they have to be compatible in terms of their signatures with those of the supertype. What do I mean by a signature? A signature of a method. What do I mean?
The declaration.
The declaration. Yeah, what parameters it takes in and what it returns. What else besides that? What else gets done and it's part of a signature besides parameters taken in and return values? There's one other key type of thing that can be done by a function by which it can signal unhappiness. It can do what? How do functions or methods in Java signal unhappiness? They throw exceptions. And that's part of the signature for many functions as well, what they throw. Okay? So this would be one thing. And this is something a compiler can check. Okay? But these these last two here are things that, ladies and gentlemen, you have to check. To write code that's reliable, that's solid, that won't break other people's code, you need to check these things manually, and you have to provide specifications that will allow other people to reuse your code, your superclasses, your car, as it were, class in a safe way themselves. And this has to do with methods of subtypes have to behave consistently with those of the supertypes, and the subtype interface has to preserve provable properties of the supertype interface. Okay. Now, these sound lofty and abstract and confusing. Let's get back to some particulars here. Okay. Just as a reflection here, often we have supertypes and subtypes that is distinguished in terms of their concreteness. So we have a car, which is a very general concept, but we have, for example, an Impala, which is a very specific sort of car, right? We may have a fruit and an orange and an apple, which are specific types. So Cavaliers, Impalas, they denote a subset of cars, right? Car might denote a whole bunch of cars out there, and the subtypes denote a subset of them. And similarly, we might have a string in Java that's a subset of objects. Object is a supertype. We can pass it around as if it's an object, but it's a subtype, right? Okay, so the rule for the Liskov substitution principle, ladies and gentlemen, having to do with the first of these criteria, this criteria here, method signature compatibility, is that subtypes have method signatures that are compatible with those of supertypes, okay? The idea here is that the subtype methods, the parameter values, can be no more restrictive than those of the supertypes. In other words, to give an example here, if the supertype has a method foo that takes, for example, a string, you could have the subtype take a string, or you could have it take an object, but you can't have it take a special type of string. They can't be more restrictive, they can only weaken. Okay, and this is very similar to the franchise situation, where we can accommodate preconditions, we can accommodate delivery of packages after noon, but we can't be more restrictive. We can't say, well, in our FedEx franchise, you have to bring it in by 9 a.m. Sorry, you're too late, buddy. You can't ship it here by 5 p.m. the next day. Okay, so let's check this out on the board here. Okay, so I'm going to erase these examples here, and we will place this on the board. Okay, so let's consider a case of this. So we have a class C, and this class C, I want to make sure there's not, here we go. Okay, so here we have a class C that has a method process, or maybe this is an interface, either one. And then we have a subtype, ladies and gentlemen, that is going to take in it's going to take in a string also, and it's going to throw the same exception, and it's, as we'll see, it will return the same thing. Is this a legitimate subtype? So this one here, we have a subtype that is exactly the same signature. Will that be legitimate? Could anyone be surprised if the subtype secretly has this signature? No, this is what's, in fact, enforced in Java. Maybe not Java 8. I've got to check Java 8 to relax this. But in Java, traditionally, if you have a supertype and you implement that supertype, you need actually a method that has exactly the same signature as this. Is that familiar to you? Right? So if you have an interface and you have my legitimate subtype 1 implements that interface, you need to provide a method that adheres to that same signature to be viewed as satisfying providing this. Is that familiar? Lou? Yeah? Okay. That is not to be assumed. I think Java 8 may have relaxed this. I'd have to go look. Certainly, quite a few other languages out there relax these constraints, okay? And we're going to see how they relax it. One way that they could relax it would be, for example, allowing process in the subtype to take an object. Could take not just a string, but an object. Any object you could give it, and it will work with that object. Why would that be a legitimate subtype? So suppose that I'm using something that apparently it seems to be a my supertype, but it's secretly the subtype that can take, for process, it can not only take a string, it can take any object. Why will I be okay with that? Why would that be okay with me? So again, we're going back to this case here, just to be clear. We're going back to this case. I have something that's secretly a D. All I know is that it's a C here, and I'm using it, and I pass it a string. Secretly, that subtype D will allow me to pass it an object. Is that going to upset me? I think it's one of these and pass it a string, but secretly suppose it took an object. Is that going to be a problem? It can take an object, but I pass it a string. Is that a problem? No, because it'll handle strings. String is just a type of object. It'll handle a lot more things. I didn't know that. I didn't know D handles, that this is a D and it can handle any object, but I pass it a string and I'm perfectly happy. It's just like me coming to the FedEx franchise at 11:59 to give my package, and they say, oh, you have till 3 p.m. Oh, I didn't know that. Well, got it to you by noon. We're still all set. I didn't know I had that extra freedom here. Secretly, it's a D. It allows more flexibility, but I didn't know that. I'm treating it like a C. I'm treating it like my super type when really it allows an object. So there it wouldn't cause a problem. Let's suppose, however, ladies and gentlemen, that subtype required instead a double for process instead of a string. Could I be legitimately upset? So I call a string and it's expecting a double. Yes, I could be. Now, fortunately, in a language like Java or Scala, this is caught automatically. How is it caught? How is this caught? If I try to create a D, a subtype, that claims it's a subtype of this interface where there's a process taking a string, and I instead have process taking a double, what will happen?
It'll yell at you when you try to compile the bytecode.
Indeed, yeah. So when you run the Java compiler on it, it will complain bitterly, right? Bitterly. Yeah. Yelling is a good term. Yes, that's exactly right. But in other languages, dynamically compiled languages, or languages which are purely dynamic in character, languages that include Python, this is not going to be caught. Until when? Begins with an R.
When it's running.
It's running, yeah. It's when it's running. Okay, so for languages which are compiled, this will typically be caught. Let's talk about some other components of this, though. Let's suppose that we want to reason not only about parameters, but about return types. Okay, so let's reason this through, and then I'll show you the rule here. Okay, so we have this in our subtype. Notice process here takes in a string and returns a string. Would it be okay if instead of a string, I returned a double? Would that be okay? No, it would not be okay. Someone's expecting a string back, and they get a double. They say, what the heck? What am I getting back here? Let's suppose instead of string, it returned an object. Would that be okay?
Maybe if it's casted when they receive it.
Oh.
Probably not.
Okay, how if it sometimes returns hash tables, and sometimes returns arrays, and that's not very good. You're counting on a string, and you're getting back this big hash table. What do I do with this thing, right? That's not going to be good. That's not going to be an acceptable thing. So, ladies and gentlemen, it will be considered a fraudulent subtype if they give you an object. This is very similar to the whole post condition thing. If they say, well, your package will get to Ottawa by 12 midnight the next day, you'd say, well, that isn't what I asked for. That's not what I'm counting on through the FedEx website. If they said that your package will be pulverized and run over by a herd of cattle and not be delivered at all, you'd probably be unhappy, at least for most packages, right? You'd be quite unhappy by that. So the post condition needs to be compatible with the post condition of the super type here, ladies and gentlemen. And the same thing with exceptions. Same thing with exceptions. So if you're expecting an exception 1, if that's the only type of exception that can be thrown based on the super type, and you're secretly using one of these subtypes as if it's one of these, all you know is that you have one of these, but it's secretly one of these guys, you need that subtype to be compatible with what you're counting on. So here, we might, for example, have a subtype that throws a subtype of exception 1. Would that be okay? Yeah, it would be. I mean, it's a subtype of exception 1. It's a special type of this exception. By contrast, if it throws a different type of exception, we're in bad news. The good news here, ladies and gentlemen, is that compilers, when we're dealing with a static language with static compilation, these things can be checked when you build your program. They're not that big a deal, and it will warn you. But be aware, as software engineers, ladies and gentlemen, that increasingly languages are relaxing this constraint. So if you have a subtype, if you have a D that is being passed around like a C, D doesn't have to have exactly the same signature for a method as C. It can have a method that's weakened in terms of the restrictions on the parameters, and that's strengthened or the same in terms of the return values and exceptions. So in other words, you can have something like this guy here as a legitimate subtype, not only this traditional one where it's exactly the same signature. This is the standard way in Java, but that's going to be changing in a big way over coming years. And already Scala, I think, allows you to weaken the method arguments and to have stricter versions of more restrictive exceptions and return values. Okay, so now let's go on to the second of these here, which will move us beyond where compilers can check. Most compilers are not going to be able to check something like this. And this has to do with the methods of subtype have to behave consistently with those of the supertype, okay? So the subtype methods here have to behave like calls to the respective supertype methods in terms of the properties, the things that you can be counting on from them, okay? And this is the basic application of the same rule as the signature rule in the sense that we weaken preconditions and strengthen postconditions, okay? Okay, so let's imagine a visitor to our franchise, to understand this, who wants to be able to rely on the guarantees they find out by going to the FedEx website, right? They shouldn't have to know all the particular quirks of this particular franchise. If someone drops off their package at this franchise, they shouldn't be rudely disappointed by the contracts there. So we're going to be talking about these, okay? About what's going on in that case. So let me ask this. So suppose you had some of this is something that stands to reason here. So suppose you had in your superclass or supertype interface, you had something that is a square root operator, and it can take in a double and return a double, and it can throw an exception, negative exception or something like negative number exception. Okay. This is behind here, but you don't need to see it. Okay. Negative number exception. Okay, so suppose we had this in our supertype, and we created a subtype, ladies and gentlemen, which had this defined, but square root operator actually performs the cube root. So this one takes it to the 0.5 power, takes the square root of it. And suppose we had an implementation of this here that had the same signature, but it actually took a cube root. Despite its name, the subtype is performing a cube root. And this throws the same basic exception, negative number exception. Would this be a legitimate subtype?
No, it's not doing it.
No, it's not doing. If someone read the interface, they read the contract they went online and they Googled this supertype, and they said, okay, this square root, it takes the square root operator. If they were secretly passed one of these subtypes, if they had code that's using this sort of code back here, that's using a C, but they secretly were passed a D, that's this subtype, where this actually performs the cube root. Could their code be broken? Yeah. Their code's counting on the properties of square root, and you're passing it a cube root. I mean, come on. You're counting on these features of the situation in terms of what square root does, what guarantees it provides. And now you're passing it something that doesn't provide the same functionality. It doesn't have the same behavior. That could break this code. So maybe for a dozen years, people have been able to count on when they get a C, it always performs the square root, and suddenly, I define a new subtype D that breaks that, where this square root operator, I implement it as performing a cube root. Then all the assumptions of foo here go out the window. And this code for foo, critically, this is very, very important. This code for foo may have been written long before I created D. Right? This might have been written 10 years earlier, before I created subtype D. And I break it just because I create a D where I don't adhere to what square root should do. Years later, I break C just because I'm not adhering to the contracts that it counted on when writing this about what the square root operator does. So the methods, ladies and gentlemen, associated with the subtype, they not only need to have compatible signatures. For example, the parameters can't be more restrictive in their types. But they also have to perform functions which are compatible with what's promised in the supertype. Do you appreciate that? Do you see what I'm saying here? And this is, square root, this is a bit of a toy example. But there's lots of cases where you might have a promise stated in specifications or implied by its name. There might be specifications, nicely preconditions and postconditions, sort of like we wrote up in those first few lectures of class. And we're counting on those about square root, and one of the postconditions returns the square root of the number. And suddenly I've created a subtype D, passed it around as if it's one of these, but this code is counting on this performing a square root, and it can no longer count on that. So it needs to behaviorally be compatible with what's promised here. Now, let me ask this, ladies and gentlemen, just to be clear. Let's suppose no specifications were provided. These were not provided. Does that help? Does that eliminate the problem? There's no specifications provided to this. All it says is square root. Does this eliminate the problem?
That's more problems.
It's more problems. Because now we're involved more in guesswork, right? Okay, I think this performs the square root. And it's not clear what's promised. It's not clear what code that's using this should be counting on here. It's when you provide some specifications that someone using this C knows what to count on. Without those, it's not clear what you can count on, and it's very easy for a subclass to break foo's assumptions. At least with specifications, these preconditions and postconditions, someone who's writing this code for foo, they know what they can count on about the superclass, and critically, someone who creates a subtype of C, i.e. D, they know what they have to adhere to. They know what their square root operator has to do to be considered a legitimate subtype of C. Does that make sense? Okay, so let's advance this, and I want to show you some more examples here. Okay, this is method behavior rule. Okay, and the final thing here is going to be provable properties, and we're going to go over a bunch of examples. But basically, anything that's provable with the supertype, in the sense that someone could convince themselves, looking at the definition of C, they could convince themselves that what's possible with C needs to be adhered to by D. Okay, and there's a couple examples of the things that are history properties or invariants. Let's look at these things. Okay, and we'll come back and emphasize it. Okay, here's our base type, counter. It has a constructor that makes it 0, and it has a get operator and an increment operator. Okay, and increment, it says increments the value of this. Now there's a bit of an ambiguity there. Increment. What do you think this means? If I say increment it, what do you think it means? This is a counter. I just increment. It doesn't take any argument. What do you think it means? Add 1 to it, probably. Now, the word increment is a little bit fuzzy, and if this had an argument n, maybe you might think it means increase it by n potentially, but it has no argument, and so probably that's what it means. Increment it by 1, right? Okay, here's a question. Is this an okay subtype? Counter 2, it's a subtype of counter, it claims to be a subtype of counter 1. It implements this interface, or it extends this class. Its constructor makes it contain 0, but increment doubles the value. Is that a legitimate subtype of this? So if you had one of these passed around to you, this supertype, if all you knew it was one of these, and then you had code that was relying on these properties, it was using this interface as if it's a counter, and secretly you were passed a counter 2, could your code be rudely surprised? Yeah, you're like counting and calling increment, it goes up by 1, and instead it doubles. You're using counter to keep track of the number of times, I don't know, you found a certain element in an array, and each time it's doubling. That's not so useful. Okay, we'll come back, may come back to a certain aspect of this that may be worth emphasizing later. Okay, how about this one? Here's counter 4. Counter 4. So in this case, ladies and gentlemen, it claims to be extends counter in this case, but it has an extra method called double value. Is this a legitimate subtype of that? So if I thought I had a counter, think back to that code for foo, right? I think I have a counter. It's this code back here. Just to be very clear, we're going through this example. I have a foo. I think it's a counter, but it's actually counter 4, and I'm using it. You know, someone's passed a counter 4 to me as if it's a counter, as if it's a C. It's really a D, a counter 4. Could I be rudely surprised by this? No, because I don't even know about double value call, right? I don't even know that it has this method. I think it's this, and I'm calling it. Sure, it has this extra functionality, but I don't know about it. I'm not using it. So this is a legitimate subtype. It extends it, but in a way that's perfectly compatible. It doesn't impair the functionality. This guy totally breaks the functionality of this, right? If you have a counter and you secretly get a counter 2, your code's going to break because you're counting on increment. Did something reasonable, like increasing it by 1, very likely, and instead it doubles it. Okay, let's go to counter 3 here. Here's counter 3. Counter 3, it differs only in that it has a different constructor. It allows you to specify any number as the starting value of that. Is this, if I were passed a counter 3 as if it were a counter, could my code break? If I'm counting on all the features of counter, if I study this and I stay up hours studying how counter works, could I be rudely surprised if secretly what's passed to me is a counter 3?
Only if it doesn't allow you to pass no arguments, just like the original.
Okay, but suppose that this is being passed like it with foo. It's being passed to me as an argument. So I don't know that it's gone through. I'm not calling. Foo is not calling here. Foo is not calling the constructor. This guy's calling the constructor and passing it to me, okay? So suppose I don't have to worry about calling its constructor. If I were passed a counter 3, could I be rudely surprised? How could I be surprised?
If whatever called the constructor passed in an argument that's far greater than what you're expecting, or just different than what you're expecting.
Okay, well, let's think about it. So I like exactly what you're saying. Your name again? Quentin. So I love what Quentin's saying here. So he's saying, suppose someone were to pass in a thing that I think is a counter. It's secretly a counter 3. And the argument is weird on it. Okay, so let's come back to it. Suppose someone passed in a counter 3, which was initialized to be 1 million. Could I be really surprised if it was just, I was expecting a counter?
Sorry, it's just containing n. Oh, I'm sorry.
Yeah,
I thought it was incrementing by n.
No, it's containing.
I'm so sorry.
It's containing n.
Yeah. Okay, so it just contains an n.
It just contains an n. Could I be rudely surprised? The answer is yes, actually. Let's try to go through an example of this. First of all, if someone created a counter 3 somewhere off in the program, right? Somewhere off here, they created a counter 3 and they passed it in to foo as if it were a counter. This is counter 3. Could foo be rudely surprised? Okay, so let's go through this. So Peggy says so no. So let's think about a million. So if someone initialized way off there in the code, they know secretly it's a counter 3, they made it a million for its initial value, and they gave it to me. So now I get a thing that's a counter. I think it's a normal counter. Could a counter be a million? Could you have a counter that gets to a million?
As long as there is no condition saying that you could.
Yeah. I mean, by this interface, sure, you could get a counter. It's initialized to 0, and you call increment a million times, right? You could get it to be a million, right? So if you give me a counter 3 that's a million, and I think it's a counter, I have no reason to be shocked or think my code is broken, that there's no way I could have gotten a counter that had the value of a million. Sure, a counter like that could have been fine produced. So my code is not going to be counting on a property that's less than a million. However, I would argue that this is not a legitimate subtype. What case is possible with this, but it's not possible with this? What could I get handed to me as a counter, secretly a counter 3? I think it's a counter, but it has a value that's impossible with this.
Negative value?
A negative value. A negative value. There's no way, given this definition, that I could get a negative value. I could with this guy, right? Okay, let's look at one more. So we have a thing that's a counter 5, and it initializes it to 0 also. And we have a method here that's decrement positive. And as long as it has a value that's greater than 0, I can decrease it by calling this method. Could I be rudely surprised? I think it's a counter, and it's actually decr positive. I'm sorry, it's actually counter 5. Could I be rudely surprised? Could I be rudely surprised by that?
With an increment, aren't you relying on it going up?
Up only. Okay, going up only. I have this certain counter, and I'm calling increment. It can only go up or stay the same in value. Then I see the same counter coming back to me later with a lower value. I could be surprised. So, ladies and gentlemen, what we're dealing with here is that things that a user can count on by looking at the subtype need to be guaranteed by the subtype. And there's two main things. We'll talk about them next time. I'll go through a bunch more examples that need to be maintained. So those issues with the arguments and the return values, so we saw the signatures, that's one thing, yes. What the behavior is has to be maintained, but also invariants have to be true. So things that are always the case, at any one time you could check, is it the case? Like it's greater than 0. Those have to be maintained. Well, let's put it this way. If those are true with the super type, you got to maintain them of the subtype. If someone could be counting on, by looking at this super type, if they could be counting on something being true as an invariant, that is always true, it needs to be true of a subtype. And second of all, any history properties, anything about compared to time A, time B, that they have to have certain relationship, like it's only the same or greater, need to be true for the subtype. Okay? These are two additional things. Any properties, in short, which I could deduce have to be the case from the supertype, need to be maintained for the subtype. Because remember, here we are, we're using a C. All we know about in the world is that there are these things called Cs. We're counting, we read, we study, we really think about their interface, and we come to some conclusions based on it. And then years later, somebody, maybe it's me, introduces a D. That D has to avoid breaking code that's counting on these features of C. Counting on the fact that it maybe never decreases, or that it always has a value above 0, or at least equal to 0, or that it has a certain behavior associated with a method name. So this is what we're going to be dealing with next time. I'm going to send you, as part of a thing probably later today, just a few examples to think about for next time. And that will be for the take-home, and then we'll talk about them next time to deal with them in much the same way we did in class. So thank you very much, and I'll look forward to seeing you on Thursday.